In the previous video, I talked about binary acids, and we had group trend considerations and period trend considerations in those acids' strengths. And now I want to talk about oxyacids. And it's a term we've mentioned before, like decomposition of an oxyacid or whatever, but the idea is very simple. It's an acid containing an oxyanion. And then, of course, we have to go back in time. Oxyanion, you got some polyatomic anion containing oxygen. For instance, nitrate, and you can throw an H on there. Oxyanion nitrate, oxyacid nitric acid. Oxyanion sulfate, oxyacid sulfuric acid. Oxyanion phosphate, oxyacid phosphoric acid. So you just take those oxyanions and stick some H's on there, and that's how you get oxyacids. And the key distinction we're looking at here between oxyacids and binary acids is that in an oxyacid, you're worried about the relationship between hydrogen and oxygen and the effect that that other thing has on it, rather than the relationship between hydrogen and that other thing directly. All right? So when we looked at binary acids, the halogens, we said that HF happened to be weak, largely because F was so close to the H, it has very small atomic radius. So the bond energy was very high, short bond, high bond energy. And when this H comes off, the fluoride ion is very small radius, and it has a high surface charge density of electrons. And as you get bigger, that factor decreases. You have 7 valence electrons in bigger and bigger spaces, so it's more stable, it's a lower surface energy as we make that ion bigger. And then as the ion gets bigger, it's also easier to remove the H because it's farther away. Now with our oxyacids, we have a very different scenario because we're not looking at how the hydrogen and that piece interact. We're looking at how this piece interacts with the oxygen to pull electrons away from the hydrogen. All right? So once again, oxyacid, we're worried about how this thing affects the bond with the oxygen and the hydrogen, versus our binary acids, we were directly worried about the interaction of the hydrogen with that thing. When we're looking, I guess, key considerations, I've already written them out here. When we're looking at what is attached, like what is that halogen, that central atom, and I say central, even though it's on the edge there as we look at these other ones, it's our central atom. We're worried about its size. If it's bigger, then its electron cloud is more spread out, its surface charge density is lower, the nucleus is farther from than the oxygen, and it's harder to pull electrons away from that hydrogen. So our goal is to get electrons away from that hydrogen. And if we were to look at this, fluorine, very strong. In this case, the nucleus is very close to the oxygen as well. So even though oxygen's a really high 3.5 electronegativity, this 4 is stronger and it's really close to this nucleus. So we're going to pull our electrons in that direction. And this is very qualitative. I'm sure someone's going to call my bluff. But when the electrons get pulled that way, then it's easier for the H plus to fall off. Now as you look at this nucleus is farther from the electrons of this oxygen, and oxygen's better at attracting electrons in the first place. So we're not going to get that strong pull away from the hydrogen. We're going to get maybe this less delocalized setup, and I say delocalized, but the oxygen's going to pull electrons more that way, probably. With bromine, it's even farther away, so that nucleus is not pulling as strongly on those electrons, and the electronegativity difference is even bigger, so it's even more staggered in the direction of that oxygen. And then you get something like iodine. This nucleus is 1,000,000 miles away, shielding effect and everything else. And then you've got your oxygen here at 3.5 versus at 2.5. And we again end up with a situation where our dipole isn't as strongly in this direction, and it isn't as easy for that hydrogen to fall off. So once again, the farther we can get these electrons from the hydrogen, the easier it is for an H plus to fall off. And the electronegativity of this halogen is going to determine how much pull there is in that direction away from the hydrogen. And the size of that halogen is going to determine how much pull there is in that direction. So as halogens get more electronegative and smaller, we get stronger oxyacids. And that's mildly confusing if you ponder our binary acids where the opposite was true, but you have to take into consideration we're not looking at the direct relationship between that and the hydrogen. This has to affect this which then affects the hydrogen. And so it kind of makes sense. As you look at our Ka values for these, the biggest halogen ion here, the biggest halogen we have, has a really low Ka value, 10 to the minus 11th. And then they go up in strength. The Ka values increase as you go up. I couldn't find a good K value for HOF, if it even exists in any meaningful way. All right, larger halogen, less of a pull. Higher electronegativity halogen, more of a pull. So you want a higher electronegativity halogen, and you want it to be smaller. And now let's take a look at how the number of attached oxygens affects the oxyacid strength. And as a quick reminder, with binary acids, we looked at how hydrogen and chlorine interacted, for instance. And now we're looking at how chlorine affects the interaction of oxygen and hydrogen. And now we're looking even more at how stuff on the other side of that chlorine affects things even more. And I think intuitively it's relatively easy to say that the more stuff you have over here, especially if it's high electronegativity stuff like oxygen, the more your electron density is going to get pulled that way, and the easier it is to remove those hydrogens. So if we look here, and I'm just going to, again, this is qualitative, kind of like my great pencil sketches over there. If we look at this, chlorine's a 3.0, oxygen's a 3.5, so we might have this situation slightly in favor of the oxygen. But as we get another oxygen over there, we start to pull those electrons more that way, and pull those electrons more that way, and pull those electrons more that way, giving this a more and more slight positive charge, pulling that charge density this way. So intuitively, I think you can look at that and say higher electronegativities, higher charge density on that side, pulls those electrons away from the hydrogen, making it easier to remove, making it more acidic. So that's one way you can look at that. And in the same note, I want to look at that in terms of what does this turn into. So when you remove an H, you get your conjugate base, these things here. And we said that you need to have conjugates that are more stable and less polar. In this particular case, that's pretty polar, right? And, well, we'll mention bond order later. In this particular case, that is, well, it resonates to be less polar. I guess you have a 1.5 and a 1.5 bond. And then as we look here, we've got even more opportunities for resonance. And I'm sorry, this looks like garbage, but I didn't budget my space well. But if you look here, we've got this resonance stabilized extra charge. We have one extra electron, and that one extra electron can be distributed over 4 locations, or over 3 locations, or over 2 locations, as opposed to it's stuck in one location. And that makes it more and more stable. So when we're talking about the stability, we can talk about resonance stabilization, and we can talk about polarity going away as we move this way, and we get things that are effectively less and less polar. So this one is polar. It's a tetrahedral base bent, and it's going to have a net dipole towards the oxygens. I didn't draw it that way. This is a trigonal pyramidal tetrahedral based, and so we've got a dipole down. And then this one is tetrahedral and nonpolar as it ends up. So it's no surprise that when we have the most electronegativities over here, when we have the shortest bond length, and when we have the most delocalization of those electrons, then we get the strongest acid. It's easiest for that H to fall off. And that's what this says right here. All right. Bond order, by the way, 1, 1.5, 1.67, 1.75. Bond order, higher bond order, shorter bond length, stronger bond, and we're crunching stuff together, which makes it even easier to pull those electrons that way. There we go.